This is just a quick video to remind you what a Fourier transform is. The reason we want to know this is because we're going to use Fourier transforms in our understanding of how filters work later on in the course. So a Fourier transform converts a signal, say a sine wave, from the time domain to the frequency domain. We'd expect the Fourier transform of a sine wave here to be a delta function. For example, if we took the Fourier transform of a top hat function, we'd get a sinc function. So if we take a look at a bit of LabVIEW code that does a Fourier transform essentially, now we're working not in an analytical environment but in a computational environment, and a Fourier transform is now referred to as a fast Fourier transform, a particular type or algorithm that's embedded within the code that does that computational step efficiently. It's quite a tricky thing, I think, when they developed it. So in our piece of example code here, we have the Fourier transform here in the middle of the code. We also have a function generator, the sine wave generator on the left-hand side of the Fourier transform here. We're able to control both the phase and the frequency of the sine wave. So actually we're able to convert it by changing the phase from 0 to 90 degrees from a sine wave into a cosine wave. We've also got control over the sampling rate of the function, so it's a digital waveform. We've got 1,000 samples per second and 1,000 samples, so we've got 1 second of data. So we'll have a graph of the signal, and then of course the Fourier transform has both real and imaginary parts. So we'll be able to plot both of those by converting the complex number here into both its real and imaginary components. We'll also look at the magnitude of the function by taking the sum of the squares and then the square root of the real and imaginary components. There's also this little function here, which we'll talk about in a minute. So if we look now at the code itself, we've got our sine wave signal on the left here, and then we've got the imaginary and real parts of the Fourier transform. We've also got the magnitude. We've got control over the phase and the frequency here. Okay, so if we run the code, we see straight away that we have both an imaginary and a real component. If we change the phase to 0, we should just have a sine wave, which we do here, and of course the Fourier transform of a sine wave is purely imaginary, it's an odd function. If we change the phase to 90, we just have a cosine function, and the Fourier transform of an even cosine function is all real, which makes sense. Okay, the issue here is really about where these delta functions are sitting, and I guess why there are two of them. Well, there are two of them because the Fourier transform is symmetric about the minus frequency and the plus frequency axes. Typically only plot the positive plus frequency axis. The reason it is centered around 500 here, if we look across to the Fourier transform itself and then what we plot, we're retaining no knowledge of the actual frequency steps that we're plotting here. We're simply plotting an array, a double array here of each of the numbers that are being computed. So there's no knowledge in these graphs about the actual frequency that we're plotting against. And so the 0 point in frequency is actually occurring here at 500, at the 500 point in the index of the array. What we're able to do, and what the Fourier transform allows us to do, is flip over that center point. So we actually now plot one of the delta function components at the frequency that it actually relates to here at 10 Hertz. And at the moment we're using a very, very low level FFT function here. If you look behind this VI, you just see a block which essentially references the algorithm itself, which is written in a different language. Later in the course we'll use higher level VIs, and they'll actually take just the first half of the spectrum, the real bit, sorry, the positive frequency component of the spectrum, and ignore the second half. And that's what we'll see. But just for the moment, we're going to use this function which flips it over so that we can see both peaks together in the center of the spectrum. Okay, so it's time to download or recreate this VI and have a play with it.